Hello, everyone. My name is Aleksandr Borzix. I am the head of pricing development department at Yandex Go. And today I'd like to talk to you about algorithms that empower our application, Yandex Go. Why do we need these algorithms? How exactly our application work? And what do you need to know about algorithms and interviewing process to excel at it? To begin with, I'd like to talk a little bit more about myself. My first job as a software engineer was when I ended the third course at university. I decided that it's a great time to start doing some development. And my first job was at the set-top box development company. Set-top box is that thing that you connect to your TV so you can receive a satellite signal, watch TV, music, movies, etc. And that was a great experience because there I had a great mentorship, and I knew a lot about C++ and thought that I'm very good at writing code in C++. I had a few friends there, and one of them decided to go to Yandex, and he successfully passed all the interviews from his first attempt. And after that, he sent me a book named Cracking the Coding Interview. And he said, "Sasha, please read all the chapters up to the sixth one before you're trying to get into the Yandex." I decided that why should I do that? I'm already good enough at writing C++ code. I know a bunch of algorithms and data structures, and I use it every day. So I decided just to do a leap of faith and try to get into the Yandex at first attempt, and I failed miserably. So I had this interview when I was given 2 tasks about algorithms, and I just had no idea how to approach them. So that's when I thought, that my friend tried to help me, but I just ignored his help. And today I want to talk to you about this idea of these interviews. What are they checking? What kind of skill sets does they really check? So after that, from my second attempt, I joined Yandex Go, and currently I'm 7 years. I have been there for 7 years now. I joined as a software engineer, and now I'm leading pretty huge department where we are responsible for all the pricing manipulations in all the Yandex Go. So the lecture plan for today is, at first we will start talking about what is an algorithm. Then we will try to define what is the problem that Yandex Go app solves. And from there, we will try to build it from the ground up, from scratch. So we will try to reinvent the wheel, to reinvent the Yandex Go. So we'll follow how it works now, how it worked before, and what are the algorithms and data structure that we use on daily basis. So those topics will be how our dispatch works, how our pricing platform works, and what kind of tools and mechanics we have to grow the demand in our service and the supply part. So let's begin. What is an algorithm? While I was preparing for this lecture, I found out that the word algorithm comes from a mathematician that was born in Khwarazm region, and his name is Al-Khwarizmi, Sorry if my pronunciation is bad. And I found it very curious because Orange region is partly in Uzbekistan land, and I wanted to share these interesting facts for me with you. But at its core, algorithm is a process or a set of rules to be followed to accomplish some problem, to solve problem. For example, you have some unsorted array, and your problem is to make it sorted. And this problem solving is the key ability that we expect from developers. And those interviews with algorithms and data structures, they're not just about how many algorithms do you know or how many data structures do you know. It's about how you approach a problem that you're given. And of course, during the solving part, you're using either algorithms or data structures. That is the key ability that is tested, not just the knowledge of all of them. And this problem-solving skill can be defined as a serious. When you approach a problem during the interview or just in the life, I think that this process consists of 7 parts. First, you need to define the problem. What are you trying to do? And to understand that. The second one is you need to analyze the problem. Maybe you can come up with some boundaries that can reduce the complexity of the problem, or you can find some insight in this definition of the problem. Then you need to develop potential solutions. During the interview, your first thought would be, oh, I know the brute force solution. It's not optimal, and it won't count as a solution, but I know that. And if you write it down and, for example, try it a few times with the input, you might see some patterns. Oh, I calculate this variable so much times, so I can just optimize it and count it one time, store it at this. It will be reduced to like a dynamic programming problem. When you came up with the different solutions, we need to evaluate them. Usually we use a time complexity and the space complexity, and it's a good metric to kind of sort them. And then you select the best one, implement it, and measure and evaluate the results, how it works. So that's the framework that you should, and I'm doing it during solving various tasks at work or at the interview. And like to use this kind of framework and use it against the problem. We will define the problem as, let's build a ride-hail app and use this framework to do that. So to do that, we need to define what is a ride-hail app. In our case, it's Yandex Go. And Yandex Go is a ride-hailing app that provides a user an ability to order a car and some driver to execute that order. And at its core, this is a marketplace where one user wants to sell something, his work, and the other one wants to buy it. And so now we can define what is the problem that this application solves. The problem we are solving at Yandex Go is we're trying to make a reliable and affordable service for passengers to meet their transportation needs. And let's define those terms, the reliable and affordable. Reliable means that if you really need a car, for example, you're sitting on your bags waiting for your flight for vacation, that will be very bad if you open the app and see no cars available, and you have no other way to get into the airport. So you lose a lot of money, have a lot of stress. And that's the reliability part. If you really need it, we need to provide you an option. The second part is affordable. Because, for example, we can make a reliable service. The prices will be so high, there will be like all the city, all the drivers in the city will want to walk with our in our application, but there will be no users that are willing to pay like $100 for a ride. So they will just sit there without any orders. So affordable part is we need to be at the same time reliable, but with a minimal cost for passengers, depending on the current marketplace state. And because it's a marketplace, we need some tools to stimulate both the demand part, passengers, and the supply part, the drivers. We need to make this marketplace efficient, like an exchange where you can trade stocks. And we define efficiency as the share of driver's time when he has a passenger in the back seat, from his total time that he is giving to our platform. For example, if he goes online at 10 a.m. and goes offline at 2 p.m., that's the 4 hours that he is willing to spend on our application. And we want to minimize the times that he needs to pick up the passenger or just when he's waiting for an order. And this last part, when he has a passenger in the back seat, we can no longer do anything with it, because that cannot be optimized. It just depends on the current road situations. So with that in mind, let's solve this problem together. Build ride-hail app from scratch. What we are building. So the passenger flow looks like you just open some app and you need to create, we need to provide you an offer. So you know where are you going. So you select the pickup point and the destination point. And we need to make you an offer that consists of the price and the estimated time of arrival. Both of these values really manipulates with your willingness to order a taxi. If the price is too high, you will just, oh, all right, I will take a bus. Or if the wait is too long, you will do the same. So that's a crucial values that we offer at this stage. So if you accept this offer, you're okay with the price, you're okay with the estimated time of arrival, that's where the dispatch part comes in. So you make an order, and at this stage, we're looking for a driver that is free and that is willing to take your order, that will accept it. And after that, that's just the tracking part, because you are matched, the driver is coming to you, and that's the most straightforward part of the application. To build a ride-hail app, you definitely need some prerequisites, some third-party services, because ride-hail really depends on the quality of your routing. Because it's very crucial for passengers to know exactly when the car will arrive and when they will be dropped off at the destination point. So you definitely need some kind of routing API. For example, Yandex Maps provide it, and we use it internally. That routing API consists of methods to calculate the route from some coordinates to another coordinates. It can give you the path on the road, and then give you jams information, the time that will take that takes to get from one point to another, and the distance. And the second part is not crucial, but it really drives our efficiency. If you have a road graph under the hood, you can use it for various algorithms that we will discuss a little bit later. But it's definitely not required, but gives you a lot of flexibility in what you're developing. So let's begin with the dispatch part. And what is the dispatch? The dispatch solves this following problem. Every order needs an assigned driver. That's very straightforward. If we look closer into this problem, we'll find that it has two sub-problems. At first, you need to find the suitable drivers for each order. For example, I have created an order from airport to the hotel. And at first, the system needs to know what are the available drivers for me. And the second part of the problem is you need to assign me one of these drivers. So we'll look at these problems in the following order, how we find the drivers and how we assign them. The first part is candidate search, as we call it. And the problem looks like I need to find some number of suitable drivers for an order and calculate their ETA. That's how it looks in real life. I need ETA because that's the key metric that affects the passengers willing to wait for the car. If it will be too high, he will just cancel an order and go by his foot or take a bus. And by suitable, we call suitable means that it's near and it has, for example, has the selected tariff class enabled that the passenger has. So if you order a comfort tariff class, the driver that will be assigned to you also need to have a comfort tariff class enabled and available. So if you analyze this problem, we'll find out that in our system, there are millions of drivers online in different geo areas. And this number grows as our service grows. So we need to do this search efficient and fast. Because other crucial part is that your application needs to run smoothly. Because if you open the app and it will take you 1 minute to calculate the ETA, nobody will use that application. And also, while you are calculating this ETA, it will just change because the road graph, road situation changed and the driver situation changed. So let's just come up with different ideas how to do that. So the most straightforward or brute force way, let's just, for each driver in our system, we can for sure do some kind of sharding. So we store Tashkent drivers in one database, Moscow drivers in another database. But in general, it looks like for all the drivers in some geo area, big one, let's calculate the route from the driver position to the pickup position. Check if it's less than some maximum available pickup distance and store it. So we will have an array of candidates that are available for this order. It's not efficient, and these routing requests to Yandex Maps, for example, it's pretty heavy because it's a CPU intensive operation. Under the hood, it generally does a search on a road graph from point A to point B. And road graph in a big city has a lot of streets, so it has a lot of edges, and it just consumes a lot of CPU time. The better way to do that, and we use this approach in the cities and in the countries that we have, where we have a poor graph, road graph quality. There are a number of spatial data structures like k-dimensional trees or some mechanics, algorithms like geocaching that can do these kind of, can solve this problem. So the k-dimensional tree is an idea when there is a search tree that splits the space by a few dimensions. So you actually can do this kind of approach for your coordinates. You have 2 dimensions, latitudes and longitudes, and this data structure will give you a pretty fast search of the nearest neighbors from some point. And as I said earlier, we use that in the countries, in the cities, where we have poor road graph quality. In some countries, so in Africa, for example. The geocaching approach is an idea when you have some coordinates and you can calculate the hash of them with the selected precision. So, for example, I want to encode this pickup point position with a precision of plus minus 5,000 kilometers. Of course, you won't do that. You will select something like the precision of plus minus half of a kilometer error. So all the points that you will encode with that precision, if they are close enough, they will have the same hash. So that gives you an idea that you can you can encode the driver's position, you can encode the pickup position, and it will be the same string. If we choose either of these algorithms to solve this problem, this gives us the following result. That's the picture of a schematic picture of a St. Petersburg, where we have a river. And the closest drivers to the pickup position by line distance, the k-dimensional tree will give us this result. So we will first find the drivers that are closest in linear distance terms, but they're actually not close at all if you look at the road graph. So we'll have 10 drivers found, calculate 10 routes to find out that the closest one in terms of a road graph situation in the real world, the closest one will be the farthest one. It's quite possible because the river, that's the place where there are no roads. It's not connected. The streets on the either sides of the river are not connected. The solution that we're using now, and the most of our geographies in the cities, is because we have this road graph, we can store the drivers attached to the vertices of this graph and use graph traversal to find the closest point, to find the closest drivers to some point. The graph data structure is actually a number of vertices, a number of edges. Edge can have a number. In our case, the road graph consists of vertices is like a intersection, the beginning of the street, and the vertices mean the distance you need to travel from this point to this point. And it's a directed graph. It looks kind of like the picture on the left. So if we will attach these drivers to the closest edge on the graph and launch some traversal of a graph, we will effectively find the closest drivers to this position. And of course, there are a number of algorithms that can do that. And you can use BFS, and that's the correct answer in this case, because we need to find the closest. So we'll first visit the closest edges, then the second closest edges in some sense, etc. And we will reach some radius eventually, a visited radius. For example, we launch this BFS on this graph from this point, and the reason to stop this traversal is when we reach the 4 kilometer radius, 4 kilometer distance from the initial point. The DFS in this case is not efficient because it will first go the depth, the farthest point, stop the climb up. It can be used, but it's not actually a good algorithm for this task. So this solution on a road graph gives us the following picture. It's the same picture of the St. Petersburg. There is a road, there is a river. Those cars are closest in the sense of a linear distance, but now when we traverse these graphs, we're not even reaching them because they're actually very far away. The second part of this dispatch problem is assignment. So we just found a number of drivers for this order that are suitable. We know the ETAs for each of them. So we need to match these orders with these drivers. As I already mentioned, the key metric in dispatch is the estimated time of arrival, because it affects dramatically the willing of a passenger to cancel the order, because usually you need taxi as soon as possible. In some cases, you can pre-order a taxi for later, but the most popular use case is when you need the car right here, right now. So this assignment algorithm needs to take into the account that we need to minimize the ETA for all the passengers. So the straightforward way to solve this problem, let's just do for each of the orders in the system, let's find the closest driver and just assign him. And that's actually an option. And for each order in the system, that's the best solution. But that's called a greedy algorithm. We know that there are a number of orders in the system. But for each of them, we make the optimal solution, but it doesn't mean that the whole system gets the optimal solution. So this greedy algorithm leads to the problem when it really depends on how who is the first to order a taxi. If I am the first one, I will get the closest car, and the person after me will have 10 minutes to wait for for his closest car. But if we solve this problem simultaneously, we had some kind of a buffer that accumulates all the orders in the system in like a 5-second window, 1 minute window. We can solve this problem optimally for the whole system. So our target would be, let's minimize the sum of all the ETAs in the system. So in this case, I will receive probably the car that's not 2 minutes away. In this case, I will receive a car that's not 2 minutes away, but 5 minutes away. It's not crucial for me. It's not 2 and the 10 minutes. But the second person will receive the car in the 3 minutes away. The sum of ETAs in this solution for the whole system is 8 minutes, where in the first one it was 12. So this is the algorithm that solves this greediness problem. At Yandex, we use Hungarian algorithm because it's very intuitive in this sense. That's an algorithm that operates on a graph where you have some kind of tasks to do and some kind of workers that can execute that task. And the value of an edge in this graph means the cost. So the Hungarian algorithm solves this problem optimally. It optimizes the sum of all the assigned orders in the system and runs in a cubic time complexity. So let's sum up what we learned just about the dispatch part of Yandex Go. So to solve this problem of finding the car nearest neighbors in the geospatial data, we use car dimensional trees. Sometimes we use geocaching approach, but for the most part, we use our road graph that is provided by the Yandex Maps and run a BFS breadth first search on it. And in the assignment problem, we use Hungarian algorithm with some tricks, of course, for a better dispatch. So more people in the system will get a better assignment. The second big problem in our application is pricing. The problem of a pricing is that we need to calculate the prices for all the passengers so they can see in advance and accept or decline the offer. It's crucial to see a price in advance as we know it. We had a lot of experiments with it because, for example, if you have cash and willing to pay with the cash, you need to know in advance how much of the cash you need. And we don't want you to be in troubles talking to the driver that you have less cash that it's needed. And it's much clearer for you as a passenger. You know all the things in advance, so you can decide, oh, that will be too much. I'm not taking the cab. So this fixed pricing idea is the core of Yandex Go today, and in the most apps, it works the similar way. If we analyze the problem of pricing, we come up with the idea that because it's a marketplace, so we have some variable demand and we have variable supply, we need some dynamic pricing. Because on this supply-demand curve, that I will show a little bit later, there is an intersection where the maximum number of trips occur. It's called an equilibrium price. So if we approach this problem and let's calculate some prices. So the pricing part would look like, let's calculate the route from point A to point B and apply some tariff settings that we have for the time part and for the kilometer part. We take time part into account because sometimes it takes you much more time to get from point A to point B because of road jams, closures, and other things, and we want to compensate the driver's time. So it has two components. Our basic pricing has two components. It's minutes and it's distance. So that's a straightforward solution. And it definitely works in the sense that solves the problem. But we mentioned that we want a reliable service, and this kind of fixed pricing does not solve this problem. And sometimes when you will open the app, waiting for your flight, willing to take a taxi to the airport, you will see no cars available. And you might be disappointed. The better solution for this problem is what we call dynamic pricing. Especially we call it the surge coefficient. So we will calculate some base price, like we did just minutes ago. But then we will apply some surge coefficient. And let's dive deeper to understand how it actually works. How do we calculate it? So this surge part is our system that analyzes the marketplace in each city at various scales. And all it does is it calculates those supply-demand ratio coefficients. And this system does it continuously and provides this data for our base price, for our pricing platform. So this coefficient might increase the price or decrease it if there are a lot of cars and less orders. So the idea of this supply-demand curve looks the following way, that we have some curve which shows us the number of passengers that are willing to pay this price. So, for example, if all the rides in the application will cost 0, there will be like infinite number of citizens that are willing to buy this ride. There will be literally 0 number of drivers that are willing to execute that order. On the other hand, if the price will be too high, there will be 0 passengers that want to use this service, and all the drivers in the city will be waiting for you. You will have the best ETA, like 1 minute, but there will be no passengers at all. And there is some kind of intersection where those curves meet. It's called equilibrium point. And in search, we're trying to achieve exactly that price on our marketplace because it means that's the highest number of trips that will be executed, that will be made in the system. So how can we calculate the search? This kind of formula, that's called a balance equation. So you literally calculate all the passengers, all the orders in some point, using k-dimensional trees, for example, then you divide it by the available drivers in this radius. You have some kind of a share. So if it's less than 0, that means that the number of passengers, if it equals 1, it means that it's perfectly balanced, as all things should be. And if it goes this wrong way, like it's bigger than 1, we need to set some cap, because we don't want prices to fly up to the roof. So we have this idea of a max surge coefficient. If it goes less than 1, it means that we can lower the prices because there are too many drivers in the area available. And this idea works, and we have it. It's called a balanced surge. But the problem with it, it's very volatile. At any given moment, you can calculate it, and it will give you different results. So you need to kind of cache it, store it somewhere, but we don't want our pricing to be cached or stored. So this approach is very volatile. So you open the app, see 100 money, then you open the app, and the few seconds later see 200, and you just don't know what is going on. So in attempt to solve this volatility, we came up with PID controller algorithm. And to be honest, I don't know how it works. But the idea of a PID controller, in simple terms, is that that's an algorithm that has feedback. So in next iteration of calculating the surge, it knows which surge it calculated in previous iterations, so he can adjust the current calculation. The idea behind the PID controller is that you need to set some target metric. In our business, we define it as the target metric is the share of free cars in some area, the share. And empirically, we found out that the 15% is okay. So at all times, we're trying to maintain this 15% free cars in some area. So this PID controller knows the target. It needs to aim to the 15%, and it knows the current situation. It calculates the current situation depending on the if it's below. It means that we need to increase the surge. So it increases the surge, and on the next iteration, it calculates it again. It says, oh, now it's the same. It hits the point. The target equals our current share. So it stops. So if the metric goes up, it effectively decreases the surge, so it goes the other way. And this algorithm, because it calculates its decision in a window, is not that volatile. It's actually non-volatile at all. And sometimes it has a lot of time to kind of grow the surge. That's the whole another problem. So to sum up, what we just learned about the pricing part is that if you want to make a reliable service that every passenger, if it really needs it, can buy, you definitely need kind of a dynamic pricing approach. And the PID controller is an algorithm that is used actually in various hardware development. That, for example, you have some temperature sensor and a radiator, so you can increase the heat if the temperature drops, or decrease the heat, etc. It's used in various ways, and that's an algorithm with feedback. The last 2 chapters will be about the demand growth and the supply growth, tools that are needed. That's not crucial, but we need them to be effective, at the same time to grow the service. So the demand growth problem is we want these tools to stimulate the demand part, and we can do this by various methods. What are those methods? The first one is the discount in the form of direct subsidy. So, for example, where we want to launch our application in a new country, in a new city, we need to provide users the price that they're willing to pay. Because when we open some new city or new country, launch there, we don't have this stable marketplace. We don't have a lot of drivers. We don't have a lot of passengers. So we need to build it. So then it will kind of regulate itself using the search algorithms, etc. So we need this kind of direct discounts. And also we need some mechanics that can lower the price. And we can do that by shortening the ride. You might see in the application that it can sometime in Yandex Go, it can suggest you to end the ride a little bit before your destination point and walk a few 100 meters on your own, because we just calculated that this pedestrian segment for you will be much faster than it will take on a taxi. Or we can shorter the ride and it will reduce the price. Or on the other hand, we can make it longer. And what that means is if you are traveling from point A to point B, and you have in the system we have someone that is traveling kind of the same way, so those orders are along the way, and if one driver will execute it, he will have a little bit of detour. So we will spend, one driver will execute that 2 orders, and the passengers will have a small detour. And because we don't need that second driver, and we don't need to pay the pickup part of the pricing, we can lower the price for 2 passengers. That's what we call carpool or combo or together tariffs. So discounts part is pretty straightforward. We just want to give people money, so we will reduce the prices using our money. And for operational managers that do this kind of tracking what's happening in the marketplace, we need to, and to be efficient, we need to be able to have a lot of various discounts that will depend on the city, that will depend on the country, on the day, on the time, on the passenger's characteristics. For example, if you are a new in this service, we want to provide you a biggest discount. If you are not a new one in the application, we want to reduce it. So in our system, these discounts look like kind of like some object that has attributes and the value. So we have any value or other value, and the discounts look like this. And we have a bunch of them. And the interesting part is that we use these discounts also in our Eats application. The idea behind the discounts in Eats application is the same, and it uses the same backend service. So if we have a passenger that opens the app, selects the pickup point and that destination point, we need to find a suitable discount. So the straightforward way will be, let's just download all these discounts, iterate through them, find all the suitable ones, because if the passenger is in the city that has no discounts, she should not get any. And select the maximum priority discount, because we have this priority thing. So if you're a newbie, you will get one discount. If you're not newbie, the second one. If you're in precisely some region of a city, you will get this one. So we have this priority thing in our discount system. So we can do this in like linear time search, but for example, in each service, we have millions of these discounts because they're created for each the product that we have in the application. So the optimal way to do that is to store these discounts as an object that has some attributes and the value in data structure that supports both priorities and this kind of search by these attributes. And that's what we call layered search tree. It has some drawbacks, but the idea behind it is that it's a fixed depth tree where each layer has its meaning. So we have a discount at the root, just some root node. And then we have the first layer in this tree that means the type of application that the user uses. So it can be Go, it can be Eats, it can be Lavka, etc. Or we have special keyword like other. So if user opens the app, selects point A and point B, and this application is Go, when we will match these discounts, we'll go the way in the tree on the path where the Go is stated. So this idea helps us find this tree, and match these discounts. At the same time, it supports this priority thing. So the second part in our demand growth tools is ride sharing. And the idea behind the ride sharing is that let's just combine some orders if they are along the way. So passengers will have slightly longer ride, but with another passenger in the car. But the driver will spend less time than executing each of them like consecutively. So driver will earn more money from those two orders. At the same time, the passengers will pay less, but their ride will be a little bit longer. So to do that, we need to take into the account that users actually want to be at the destination point as soon as possible. That's the idea behind why we're trying to minimize the ETA. But in some cases, user can accept a detour of a 5 or 10 minutes to wait a little bit longer in exchange for a discount. But it also means that our algorithms that does this ride sharing, that matches those orders, need to take these detours into account and not exceed this detour value for each passenger. And there are no slides about how we do that. In general, to match two orders to a single driver, we can do that effectively. That's not a big issue. The problem comes when we are trying to solve the problem. For example, we have 10 cars in the city and 10 orders, and we know that we can combine them any way we like, and we want to efficiently, it means spend the least number of drivers' time, the supply hours, to execute those orders. And this kind of problem is called VRP problem. That's the general problem of traveling salesman problem, if you've heard of it. And that's a kind of problem that is NP hard. It means that there is no optimal solution for this problem in polynomial time. And we have some solvers, for example, in our logistics department or in market, that because they are solving this, their everyday task is to batch hundreds orders to one car and effectively get them to the users. But in general, this problem is unsolvable in polynomial time. And that's an interesting idea in computer science. That's where various heuristics, various approaches comes into play. And for example, in our ride tech, we also try to solve this kind of problem to build intercity. If you heard about this product in Yandex Go, when you can travel with other co-riders, and the number of these co-riders can exceed 2. So at best, we're trying to do the matching for 6 orders, so they will be in one car. The last part is supply growth. The idea behind it is if we grow our supply, so we grow the number of hours that drivers are spending in our application, it means that we can execute more orders, and more. It means that the surge effectively will be lower, more passengers in the city, and this marketplace will work even better. So we need some tools to grow these supply hours. And the last thing that I want to talk about is the idea that if we look at the working day of a driver, he usually starts at home, he opens the app, goes online, but then the series of orders can lead him anywhere. And by anywhere, I mean literally anywhere. He can end his working day very far from home. It's especially a thing in Moscow, when there is a Moscow region that is very big. So driver, to compensate this thing, needs to go offline a few hours prior to the time that he is willing to go offline. So he can just go offline, travel home without any order, and rest, end his working day. So we have this system that we call a reposition that takes the driver's preferred destination into account. It looks like this. So driver at any point in time during the day can set that he wants to travel home right now, and he doesn't need to go offline because this order can lead him farther away from home. And this reposition thing is a part of our dispatch algorithm that we discussed a little bit earlier. And what it does is if driver has a selected preferred destination, it can be a point, a home. It can be a region that's called my district. It looks like a circumference, a circle on a map. So he can say, I don't want to leave this circle. For example, because I have a kid at school and I have a few hours to work nearby. So please don't give me orders that make me leave this region. So that's the idea, that's the service that we're developing that boosts our supply hours, and it grows our supply because now drivers can, if they have a preferred destination, if they're ending their working day or just waiting for something in some region, they can use this time effectively. And our reposition service, all it does, it filters all the orders for these drivers. So reposition makes them not suitable for orders that doesn't meet this criteria of driver's preference. So to sum up, I want to a little bit talk about what I just told you. At first, I want to say and highlight it that these problem-solving skills that are algorithms used, where algorithms and data structures are used, they definitely require training. So even if you know all the algorithms in the book or all the data structures, it doesn't mean that you can solve any task at an interview or a job. It doesn't mean that. So effectively, to excel at the interviewing process, for example, you need to know some basic algorithms and data structure, but you need to train this skill to combine them, to identify the problem, to generate the solutions, to speak with the interviewer. That's a crucial part in this interviewing process, because when you are approaching this problem at the interview, you're not alone. There is a person that you can ask a question, for example, can I assume that, and give your hypothesis, and there is a person that is effectively trying to help you get through this interview, and it helps you solve your problem. Also, we discuss various algorithms and data structures that we use every day and tune it in different our new products and projects. So we talked about graphs, especially the road graph that we use, and trees, and various algorithms that we run on them. We talked about greedy algorithms and why they're not the best solution in every case. And we are trying to, in our system, don't use that. Also, we mentioned that there are a number of problems that currently have no optimal solution and probably won't ever have. So we need to come up with some new ideas how to solve them in some measurable time. And also, we just walked through our application, various parts of it. We discussed how an effective dispatch can be built and what is required for it. And also we created this. We discussed the pricing problem and created the effective pricing that we use every day, but there is still some things that we are tuning for various new markets, or we just every day monitor how it works and try to do it better, try to solve those problems in a better way with more efficiency. Thank you very much for your attention.